Right. Good afternoon, students. So we're going to start. Right, the plan for today is to finish up topic 3. Right, definitely will happen because we are at the last few slides. Then we'll start on topic 4. Okay, then tutorial 3 we'll go through tomorrow. Okay, so hopefully you have some time till tomorrow to try out the tutorial questions. Why is there so much echo? Okay, yeah, so just a quick recap. Basically, we have derived this table of derivatives already. I don't know, there's a lot of echo. Hold on. Test. I think this one good. See, the echo is not that bad. Feels like singing karaoke with all the echo. Yeah, so as I was saying, right, the table of derivatives being shown here, we have derived each and every one of them. Okay, I mean, at least for the differentiation rules of the various functions, okay, all the way from constant to the inverse trigo functions, right? We have gone through the derivation already. So it all boils down to this principal formula here, which is just trying to evaluate the limit of a gradient, of a slope, okay? So this whole thing is just the slope of the tangent, okay? So basically derivatives are just trying to find the slope of a tangent. Okay, so the slope of the tangent is the instantaneous rate of change of a function, which is defined as the derivative. Okay, so well, this is good. Okay, so we'll be using this table in your midterms, right? Of course, you'll be tested on the usage of the differentiation rules here. Okay, so to me, differentiation is more about practice. Okay, all the product rule, quotient rule, chain rule, whatever rule, logarithmic differentiation and whatnot, right? Okay, so those are just practice. Okay, so you practice more, you are going to be able to solve those things, right? Because there is what we call a standard procedure. Okay, when we ask you to differentiate a function, it's not like an open-ended problem where you are supposed to apply kind of critical thinking. There's no critical thinking here, right? As in you just apply the formula. Make sure you know how to use the formula, okay? Which is has been demonstrated in the various examples. So now we are going to look at the concept of differentiability. So differentiability is an extension of continuity. And we understand continuity intuitively, right? Because continuity is really just, are you able to draw the curve in one stroke across a point? Okay, let's say the point is at x equals to a, for example, this point here, right? And we dealt with continuity before already. Okay, and that is, if you are able to draw across that point in one stroke, then we say that the function is continuous at point A. And the mathematical definition is the limit must be equal to the function value. The limit must be equal to the function value. Okay? So certainly continuity is a prerequisite of differentiability, because differentiability means the smoothness of the function. Okay? So if a function is differentiable, then we say that the function is smooth. So this got to do with smoothness, okay? Smoothness of a function. So you can see here that in order for a function to be smooth, or in order for a curve to be smooth, in order for a line to be smooth, at any point, right, you must not have a sharp kink, okay? So if you have a sharp kink, or what we call cusp, then the function is not smooth at that particular point. So for example, what is not smooth? This is not smooth. Okay? So you can see here, at this particular point, right, it is not smooth because there's a sharp edge. Okay? So whenever there's such a point there, we say that it is not differentiable. Okay, so not smooth means not differentiable. Okay? So which implies that in order for a function to be differentiable at some point, the point must be smooth. But what is smooth? Smooth means the tangents must be collinear. Okay, because when we say differentiable means, because when you are able to differentiate, that means there is a slope of a tangent. So the tangent must exist in the first place, right? So at some point A, how can the tangent exist? It must be such that the tangent on the left must be collinear with the tangent on the right. Okay, I repeat that again. In order for a tangent to be present at point A, the tangent on the left of A must be collinear with the tangent on the right of A. So that is given by this relationship. You can see? Okay, so you can see, if you take the limit as x go to A minus just before point A, right? This tangent is represented, the slope of the tangent is represented by this blue line here. Okay, then correspondingly on the right of A plus, you can see that as x approaches A plus, just slightly to the right of A, this tangent f prime, the slope of the tangent f prime must be for this tangent given by the red line. Okay, so when the two tangents are collinear, it means the blue tangent slope is equivalent to the red tangent slope. The slopes are the same. All right. So therefore, in order for a function to be differentiable, first of all, we got to make sure that the function is continuous in the first place. Then subsequently, we just check whether the f primes are the same. Okay, before and after the point. Is that right? So let me demonstrate. So let's have an example first on the concept of non-differentiability. Okay, so which of the function below is differentiable at x equals to a or t equals to a? So we just try to justify using the two conditions. So you look at the first example, which is the unit step function. Okay, now unit step function, right, actually is discontinuous. So the continuity condition is violated. Okay, so you can see that at t equals to a, function is not continuous, right? Not continuous. Okay, so therefore not differentiable. So the unit step function is not differentiable simply because it is not differentiable, it is not continuous at x equals to a or t equals to a. Is that right? Okay. So but you do notice that actually it satisfies the second condition, right? The second condition is that the tangents are actually of slope 0, right? Because before a, right, what is the slope of the tangent? 0 ma? Correct or not? Then after a, right, what is the slope of the tangent? Also 0. 0 equals to 0. Okay? But however, it's not continuous in the first place. So therefore, there's no need to check the second condition already. Okay? So what about for the second function, the absolute value of x or modulus x? Now you can see that at point x equals to a is continuous. So the first condition is satisfied. Continuity is satisfied. So it's continuous. But if you check the second condition, it doesn't satisfy. Okay? So you can see that the tangent before, so the tangent before point A is downward sloping. So what's the slope? The slope, right, is actually -1 because you can differentiate this. Okay? So from here, you can see that if I do a f prime x, so you notice that before x equals to 0, this is giving me -1 because differentiate minus x with respect to x. Then differentiate x with respect to x is 1. So this is x less than 0. This is x more than 0. Is that right? Okay. So you do observe that at x less than 0, you have a slope of -1. So this implies that the limit as x approaches 0 minus on f of x, right, is -1. It's the blue guy because it's a blue tangent. But if you compare it with the tangent that is on the right, maybe I use green color, this tangent. That tangent has a slope of 1. So this guy is for the tangent that is on the right of A, right of 0. So therefore this is not equivalent to the limit that when x approach 0 plus on f of x, which is equivalent to 1. -1 is not equals to 1. So obviously, as discussed earlier on, there's a sharp point there. So therefore, the function is not differentiable. So not differentiable as well. Okay, so the reason is because tangents are not collinear. Is that right? So that's for the second absolute value function. Then for the last function, sine 1 over x. So this guy is also not differentiable. You may think it's differentiable because it seems to be like a continuous wave, right? Continuous oscillating sine curve approaching the point x equals to 0. In this case, a will be 0 lah. Okay? But because the fluctuation, the frequency of the fluctuation at x equals to 0 is kind of infinity. So which means that actually the function is undefined at x equals to 0. So if the function is not defined at x equals to 0, how can it be continuous in the first place? Because the function value is not defined, what? And continuity requires the limit, right, to be equal to the function value. Is that right? Okay? So therefore, this is not continuous. So this part, right, it fails the continuity test. Okay? So the reason is simply function is not defined. Okay? F of 0 not defined, cannot satisfy continuity condition. Right? So not continuous means what? Not differentiable. So in a nutshell, we need smoothness. If you can have the graph, then it's quite easy to see. But sometimes we don't have the graph. Okay? So the same logic, the same concepts here are applied to multivariable functions as well. Functions of 2, 3, 4 variables, etc. So when you are given a function of, for example, 3 variables, it's not possible to graph. There's no way to graph a function of 3 variables, f of x, y, z. Right? So just now I was asked a question that what's the topics for after the midterms. After the midterms, you'll be focusing on multivariable calculus, which means the differentiation and integration associated with functions of more than one variable. More than one variable. Because you notice or not, so far all the functions that we are dealing with, right, is just one input, f of x, f of t, g of t, h of x. There's only one variable. So then the concepts here will be extended to multivariable. Okay? When it's multivariable, the visualization is not so easy because it's kind of difficult to graph a multivariable function. 2 variables still okay. I will try to graph. Okay, but 3 variables not possible to graph because we live in a 3D space. It's not possible to visualize 4 dimensions. Okay? So therefore, that's why these mathematical tools of checking conditions apply, right? For cases where you cannot visualize the graphs anymore. Okay? By the way, I'll give you a warning first. From topic 5 onwards, let me think. 4, 5. Sorry, from topic 6 onwards, which is the beginning of multivariable calculus. Okay? Which means after the term break, right, the difficulty increases dramatically. Okay? Right? I take it as you're up for the challenge because I saw your quiz 1 results. I thought it was pretty good. I saw quiz 1, wow, the mean quite high. I was quite happy. Sorry? The average is 7 upon 11. So 7 is quite good. I mean, as compared to the last year's result, right? Your class was pretty good. Okay? Yeah, so hopefully you're up for the challenge. Yeah, I tell you first because you have to prepare. Okay? During your term break, don't take it too easy. Right, so now we apply the conditions on this given function. Right? So you're just going to determine the parameters A, B, C in order for the function to be differentiable in R. And we'll also verify in Desmos. Can Okay? Yeah, so we have 2 conditions, correct or not? So the first condition is ensure continuity. Right? Ensure continuity. So how to ensure continuity? Now you notice that this ax squared plus b sine pi x plus c itself is continuous, what? Correct or not? So the first function is continuous in the interval. Okay? So let's write. Notice both functions are continuous in their own intervals. So we checked. So we enforce continuity at x equals to 0. Okay? So it's only at x equals to 0, we need to make sure the two functions are continuous. Okay, which is not difficult because we're just going to make sure that the left function, so maybe I underline in blue, must be equal to the right function. Okay, left function must be equals to the right function at x equals to 0. Okay, so which means that the f of 0 must be equal to the limit as x approach 0 minus on f of x, right? So this guy is really just the blue function. So it's a times 0 square plus b sine pi times 0, which is 0, plus c. So the end result is just c. Is that right? Okay. But this guy got to be equivalent to the limit from the right. Okay. So this guy must be equivalent to the limit as x approach 0 plus. But on the right of 0, you have to use the ln function. So this is really ln 0 plus 1. I mean, if you can do direct substitution and you get a limit out, then that's the answer. So therefore, since continuity must be enforced, so you have c equals to 0 then. Okay? Right? As I mentioned, limit must be equivalent to the function value. C must be 0. There's no choice. Okay, so after we have ensured continuity by making C to be 0, then we are only left with A and B to determine. But we have not ensured the collinearity of tangents yet. Okay, so therefore we need to differentiate the function. Can? So therefore now let's differentiate the function. So we just do a d dx of the function. So then we have our f prime x. So our f prime x will be just differentiating each function respectively. So you have 2ax plus pi b cosine pi x. Is that right? So in the meantime, in the process here, right, I use chain rule. If you didn't realize, sine differentiate cosine, then multiply by the derivative of pi x with respect to x. So therefore, I must have a pi multiplied. Can? So therefore, this guy will apply for x less than 0. Okay. So then the second function, right, will be just 1 over x plus 1. Because you differentiate ln, so it's just 1 over x plus 1. Okay. Then you, by right, supposed to use chain rule. Differentiate x plus 1 respect to x. Then it's a 1, no? So you multiply by 1, it's the same expression. So this guy will be giving you x more than 0. Is that okay? Yeah, so after we have evaluated our f prime, then we just make sure the f prime at the top equals to the f prime at the bottom so that the tangents are collinear at x equals to 0. That's all. Okay? So therefore, let me just copy and paste this thing. Can okay? So now second, sorry? Oh, no. Good question. Okay, so one of you asked, right? Why is this not less than and equal to? Because we have not checked whether there is a tangent indeed at x equals to 0. Meaning to say, let's say for example here, okay? Before x equals to 0, we have gradient of minus 1. After x equals to 0, we have gradient of 1, slope of 1. Can you see? Slope of minus 1, slope of 1. But the slope of minus 1 and 1 does not apply for x equals to 0. Even though there is a continuity here, meaning to say the function is defined at x equals to 0, which is 0. Okay? But when you differentiate, right, you must remove this equality sign. Because when you directly differentiate, you are not certain that the two functions will give you the same value at x equals to 0, which means that you are not sure at that time, right, whether the slope are the same on the left and the right. So therefore, you have to remove the equality sign, like what I did here. Only after you check that, oh, I want the slope, if the slopes are equal, then you add in the equality sign, because the tangent is the same tangent as that on the left and the right. Understand? Okay? Yeah, so therefore, I remove the equality sign here. Okay, but I'm going to enforce that equality sign because I'm trying to find the values of a and b such that you have that same tangent. Okay, so ensure collinearity of tangents. Okay, so this one, same thing lah. So just take limit x go to 0 minus. So 0 minus is the blue function. So let me just change this to blue. Okay, so therefore f prime of x, so this guy must be equivalent to 2a times 0 plus pi b times cosine pi times 0, which is cosine 0. Okay, so it looks like this guy is going to give me pi b. Okay, so that's the tangent that is on the left. Then now we just repeat the same story for the tangent that is on the right. So limit x go to 0 plus on the f prime. So this guy will be giving me 1 over 0 plus 1. Okay, so this guy must be equivalent to 1. Okay, and then left must be equivalent to right, must be collinear. So therefore, I must have pi b equals to 1. So that means that I found my b already. So b is 1 over pi. So only when b is 1 over pi, only when you have b equals to 1 over pi, you have the tangents being collinear. That means smooth. Okay, so this guy is for smoothness. So then you notice that there's no constraint on a, because you only solve for c equals to 0 and b equals to 1 over pi after you have ensured the smoothness and continuity at x equals to 0. So that implies that a can be anything, okay? Because two conditions satisfied already, right? So since no constraint on a, so a can be any real number. A is an element of all real number. Okay? Yeah, so I'm going to show you the graph. Okay? Yeah, so let's plot the graph together and you will see when you mess around with the ABC, you're going to get. Okay, now let me enter. So the first function, right, is ax squared plus b sine pi x plus c, yeah? Okay? So ax squared b sine pi x plus c. Okay, and this is applied for x more than and equal to 0. Oh, sorry, less than. Okay, so can you see the function there? Right, and of course, a, b, c are given as 1 now. Then let's look at the right function. So the right function is just ln x plus 1. So this applies for x more than 0. Okay, so you can observe that the functions are not discontinuous at x equals to 0. Okay, currently for these a, b, c values, right, the functions are discontinuous at x equals to 0. Okay, so for continuity, you must have c equals to 0. Can you see that? Once I put c equals to 0, it becomes continuous, but it is not smooth. Okay, not smooth because you can see that there's a sharp point here, right? So because for continuity, we only found c equals to 0. Okay, so that is indeed what we observe. Then b must be 1 over pi. So you can see, once you have 1 over pi in b, right, if you zoom in here, you can see that it becomes collinear. If you zoom towards this part, right, you'll see that this is smooth. Can you see? It's collinear. It forms a straight line. Is that right? Okay? So then we would also like to verify that A can really be anything. So if you just mess around with A, it doesn't matter what's A, right? It doesn't matter what's A. You always have this point, right, being smooth, regardless of what A is. Is that okay? So that's indeed the solution that we discover, okay, through the enforcement of the two smoothness conditions, differentiability conditions. Is that okay? So this is about differentiability. Can okay? Right, so yeah. Because, okay, why is it that there's no constraint on A? Because for the function to be smooth, you only need to be satisfying the continuity condition and the collinearity condition. What? No other condition already. From the graph, we can tell, right? Once you have the connection of the curves before and after, and you also have them being smooth at that point, then that's differentiable already. No other extra conditions to satisfy. So therefore, when we solved for the values of A and B and C, right, ensuring the two conditions, we realize that we only get C and B to be certain values. Then A is not involved. So if A is not involved, that means A can be anything. No. It depends on the function. So in this case, it depends on the two functions being given. If I give you different function, then A, B, C will certainly be of different values. It's more of enforcing the condition to solve for the unknowns. Is that right? Can Okay. Yeah, higher order derivatives. I think this one you also have seen before because I think in your physics class, right, you already differentiated the velocity to get the acceleration. So differentiate displacement, get velocity. Differentiate displacement 2 times, you get acceleration. So certainly you can keep on differentiating. Okay? So therefore, if you have higher derivatives, then usually I would like to write f prime prime, f prime prime prime, and so forth. Okay? Then the shorthand for differentiating n times is you have this bracket n. Okay? So that's a universally accepted notation for the nth derivative. So this is something that we have that I've discussed earlier on. Okay? So basically, what is the meaning of acceleration? The meaning of acceleration is the rate of change of your velocity. Okay? So therefore, having understood that, you can see that if you look at the displacement curve, right, you actually know whether the object is accelerating or decelerating. Okay? Because you can visualize the tangent. So imagine that the tangent, which represents the velocity, the slope of the tangent represents the velocity, right? Because you are doing ds dt. Now at t, right, you have a shallow sloping up tangent, right? Which means the velocity is somewhat not that fast. Okay? As compared to after, at a later t plus h, right? After some time has passed. Now you notice that your slope is now steeper. Okay? So when you see that the curve is curving up, right? That means it is having a positive acceleration because your velocity is increasing. Can you see? Okay? So therefore, this has to do with the concept of whether the curve is curving up or curving down. Curving up or curving down. Okay? So if the function is curving up, the curve is curving up, then we call that a convex function. Then if it's curving down, we call that a concave function. Okay? So curving up or curving down has to do with whether your optimum point is a minimum or a maximum. Okay? And that we are going to revisit in Math 3. Okay? So we're not going to deal with concavity now. I just tell you that there's a deal with the function curving up or curving down. So now, exercise. So we have an object that moves with the displacement function below. Determine its velocity and acceleration function. Derivative of the acceleration function is called jerk. And you're supposed to explain whether this name is appropriate. Okay, whether jerk is appropriate. We'll discuss this in a while. So let's look at the velocity. So easy peasy, s prime t. So this one should be like giveaway kind of question. So now, t cosine pi t, product. So use the product rule. Okay, whole t, differentiate cosine pi t. So you get minus pi sine pi t. So obviously I use chain rule, right? Plus differentiate t whole cosine pi t. So that's the answer. Can I? Okay. So then subsequently, you want your acceleration function, a of t. So a of t is really v prime of t. It's really s prime prime of t. It's the same thing. Okay. So from here, you notice that you have minus pi t sine pi t. Okay. So maybe I take the minus pi out. Then I multiply by. So t sine pi t, I can have t times pi cosine pi t plus sine pi t. Okay? Then the cosine pi t, I'll just leave it. Oh, sorry, I need to differentiate that. So therefore, I get minus pi sine pi t. Okay? Now, because the first term is once again a product of two functions, so certainly I need to apply the product rule one more time. Is that right? Okay, so it looks like you can simplify that expression. So you can just take out the minus pi, which is present in both terms. So you notice that there is a plus sine pi t here. Did I mess up? This is a plus. Huh? You're right. My bad. Okay. So this one, minus pi, I factorized out already, correct? So therefore this, wait, t sine pi t sine cosine, this is correct, what? Minus pi sine pi t, yeah, this is also correct. So if I put, okay, I see. Okay, maybe let me just write one more step. So this thing, right, is here. Then because I factorize out the minus pi for this second term, so it should be a plus sine pi t here. You see, because I factorize out that minus pi. See that? Okay. So therefore, that gives the answer that is given here. Okay, so this is my acceleration. So if you were to differentiate acceleration one more time, then you're going to get this thing called jerk. Okay, so the j of t, this guy is a prime t. So if you differentiate one more time, right, you're going to get jerk. Okay, but there's no need to do so. The main thing is, why is the acceleration derivative called jerk? Why is the acceleration, the derivative of the acceleration called jerk? Okay, so you need to use your imagination a little bit, right? So imagine, okay, now let's say you're standing, right? And you may be undergoing a huge acceleration. Let's say let's say you are in a car, for example, Tesla Model S, for example. Okay? So now you're undergoing full throttle. Then you undergo a very high acceleration. So what's going to happen, right, is that you're going to be like stuck to your seat, right? Correct or not? Okay, so if the acceleration value is very high, then you are just stuck to your seat. Agreed? Okay? But then you notice that if the car suddenly brakes, what happened to the acceleration? I repeat my question. If, let's say, the Tesla Model S is accelerating, then suddenly you brake, suddenly the driver brake. So then the acceleration suddenly changed from a very huge value to maybe zero or to maybe negative. So which means that when you are stuck to your seat originally, then suddenly, right, the driver brakes and there's a huge change of acceleration and you are being jerked forward, okay? So you can see that as the acceleration changes, you experience a jerking motion. As acceleration changes, right, you experience a jerking motion. So the bigger is the acceleration change, the bigger is the jerk. You observe that? Okay? So therefore, right, the rate of change of acceleration is called jerk. Can Okay? So let me write down the explanation, right? When acceleration changes abruptly, is that spelling correct? Correct, Okay? When acceleration changes abruptly, you experience a jerking motion. Okay. So indeed, jerk equals to the rate of change of acceleration. Because when acceleration changes abruptly means what? Means acceleration changes within a very short span of time. So you just have to imagine, right? Let's say you sit in a car, then the driver, right, accelerate. That means the driver keep on tapping on the acceleration pedal. Like, you're like, so what do you experience? Right? You keep on jerking back, right? Correct or not? Right? If the driver just repeatedly step on the accelerator, then it's like, So you keep on getting jerked backwards, what? Or jerked forwards, okay? And it's also the same thing if the driver brakes on, steps on the brakes repeatedly, brake. Then you just get jerked forward. Okay? So understand, huh? Okay? So that's why they name the derivative of acceleration jerk is exactly the motion that one is going to experience. Okay? So it's not like anyhow. Alright? So hopefully you get some physical meaning or physical understanding from the derivatives. Okay, now L'Hopital's rule. So we go back to limit evaluation, and this is the most powerful method of evaluating limits. L'Hopital's rule, most powerful method. Okay, if you can use it, if you are allowed to use it, you should use it. Okay, because it's usually very simple. So let's look at how we can use L'Hopital's rule. Okay, now imagine that you have this limit to evaluate, which is f over g. Now, when the limit of f is equal to 0, and the limit of g is also equals to 0, now what happens is that you get an indeterminate form, 0 over 0. Okay, so this is the problem that we had in topic 2. Okay, so now, look at this process. Now, I can rewrite f over g as f minus 0 over g minus 0. Okay, still f over g, no change, right? I can also multiply by 1 over x minus a at the numerator as well as the denominator. Okay, so this cancels off to be 1, right? So eventually this limit is still the same limit, no change. But why I do that is because this x minus a, right, you can treat it as the denominator in the numerator term. You see, f of x minus, but 0 is what? 0 is f of a, okay? So, let me underline. So this 0 is f of a, okay? So we have, can see here, right? So if this limit of f of x equals to 0, right? What does this 0 mean? This 0 is f of a. Because you do direct substitution. Okay? If you do direct substitution, you put a inside f, right? You get 0. That means that 0 represents f of a. Then the same goes with g. So g of a is also 0. Okay? So I can write it like that. So, but the magic of writing it like that is that, right? You notice that actually the upper limit is your f prime a. Isn't the upper limit your f prime a? Correct? Then the lower limit is your g prime a. Because, what is this? This is the slope of the secant line, what? Between x and a. Can you see? So therefore, as your x approach a, you are trying to get the slope of the tangent line at a, at point a. Okay? So therefore, this whole limit, right, is f prime a. This whole limit is g prime a. Sorry? Okay, no problem. So this part may be a bit fuzzy. Okay, let me explain. Okay, from here to here, okay or not? Can? Okay, I believe this part is not so clear. So let me explain. So let's say this is f of x. Okay, so let's say, okay, let me put f of x on the x-axis. So f of a is 0, right? Here. So you get 0 over 0, the indeterminate form. So this is a. Okay, so f of a is 0. Can you see? So where is f of x? F of x can be anywhere. So let's say this is x. Okay, let's say this is x. So therefore, this point, right, must be the function value evaluated at x. So this point is f of x. Okay? So now, we know that this f of a is 0. F of a is 0. F of x is some function value evaluated at x. So, what is this ratio? This ratio is the gradient of the secant line, what? Can you see? This secant line, right? So the slope equals to f of x minus f of a divided by x minus a ma. Isn't that correct? The slope of the secant line. Okay? So therefore then you know, if we take limit x go towards a, what does that mean? That means you are looking at the slope of the tangent line. Because x now has to go towards a. So now it becomes like that. Correct not? This is the tangent ma. So therefore what is the slope of the tangent? It must be taking the limit x go towards a on the slope of the secant. Is that right? Okay. So this is the slope of tangent. How about that? Okay. So slope of tangent is just f prime. So therefore it's just f prime evaluated at point A. Can you see? Because you are trying to find the tangent at point A ma. Correct not? The slope of the tangent at point A. So therefore this is f prime A there, f prime A. Okay. So if you understand this, you can also extrapolate to g prime A. Is that right? Can Yeah, so therefore, you do observe that, right? If you get a 0 over 0 limit for f over g, then basically what you can do is differentiate each of the function f and g, right, on their own. Then after that, re-evaluate the limit again. Okay, and you can do this as long as you have 0 over 0. So let's say, after you differentiate one time, right, you still get 0 over 0. Then never mind, differentiate again. So you keep on differentiating until you get the limit, okay? But sometimes the L'Hopital's rule does not work, right? Because it is possible that for certain functions, right, you can like keep on jumping between the same functions that you will not get the limit to be evaluated, okay? So when that happens, then you have to fall back to the other limit evaluation methods that we have covered in topic 2, okay? So this is the idea of L'Hopital's rule, okay? So for example, let's say now you want to evaluate the limit x squared minus 1 over x minus 1. I know this one easy. You can just factorize and divide off and then sub in, okay, to get the limit, right? But you can also use L'Hopital's rule. Because if you do direct substitution, then obviously you get 1 minus 1 ma, then over 1 minus 1, which will give you the indeterminate form 0 over 0. Okay, so therefore this is the condition to use L'Hopital's rule. So you see, I just differentiate x squared minus 1 to get 2x, which means differentiate separately. Don't go and use quotient rule. Okay, this one, d dx to get 2x. Then this is differentiating the numerator. Then the denominator also differentiate to get 1. Differentiate x minus 1 with respect to x. You get 1 ma? Agree or not? Okay? So don't use quotient rule, please. It's not quotient rule. Differentiate separately. So you get 2x over 1. Then now you sub. Sub x equals to 1. You get 2. So that's the correct answer. Okay, if you use factorizing and dividing off, you also get 2. Because you have x plus 1. So 1 plus 1 is 2. Okay? So that demonstrates the use of L'Hopital's rule, right? Just by differentiation. And more powerfully, L'Hopital's rule also applies for another indeterminate form, which is infinity over infinity. Okay? So basically this is the derivation, right? So a bit lengthy, so I'm just going to go through quickly. So you see, now if let's say your f gives you plus or minus infinity, same thing, your g also gives you the limit plus or minus infinity. Then if you were to sub in, right, you are going to get infinity over infinity. So that's indeterminate. Okay, but you can rewrite this f over g as 1 over g divided by 1 over f. Same thing, okay, f over g is the same as 1 over g divided by 1 over f. Then I'm going to name this 1 over g p. Name 1 over f q, okay? Now, what's the purpose of doing that? Now, because when I write reciprocal, right, I realize that I get from infinity over infinity to 0 over 0. Because it's 1 over infinity ma, correct not? 1 over infinity, because I sub in x equals to a, I'm going to get 1 over infinity, which is giving me 0. So let me just write down here in case it's not clear. So this guy is because you get 1 over infinity. Because 1 over, okay, because g is plus minus infinity. So the same thing goes for f. 1 over infinity also give me 0. Can right? So, if I get 0 over 0, then I can use L'Hopital's rule, because I just proven in the earlier slide that once you get 0 over 0, I can use L'Hopital's rule. Okay? So which is what happened here. You see? So this limit L, applying L'Hopital's rule, I get P prime over Q prime. You see? P prime over Q prime. But because P is 1 over G, so therefore I have to use the chain rule. Can you see? So which is going to give me minus G prime over G square. Because this one 1 over G, so differentiate, right? You're going to get a G square at the denominator. Then your chain rule is going to give you G prime. Same goes for F. Okay? Or same goes for Q. Right? So from here, right, I can rearrange. So you can see that I can put all the prime terms together. Minus G prime over minus F prime. The minus will divide away. Then I get F square divided by G square, which is the second term here. Can? Okay, so then applying the limit on the two fractions separately. So the first term is just L square. Okay, because why is it L square? Because the limit that you are trying to find in the first place is this. This is this. This thing inside the bracket is L. Okay? Can you see? This is L, so this whole thing is L what? Then L square. L square? So then you notice L equals to L square. From here, L equals to L square times this limit. So you see that this guy is equivalent to L. Because this is the L. So guess what? You just have to invert. You see? L square times this limit equals to L. Then your objective is to find L, correct not? So therefore you get 1 over of this limit. 1 over of this limit. Can you see? Okay, so when you solve this, you are going to get this expression. Can? Because L square over L, then you're going to get 1 over this limit. But 1 over that limit is just when you reciprocal the fraction. So it becomes now F prime over G prime. So then we found that, so indeed, if you have the indeterminate form, infinity over infinity, you can also just differentiate the numerator and the denominator separately. Okay? So L'Hopital's rule applies for the two cases, 0 over 0 and infinities over infinities. Can? Okay? So in the event that you don't get any of the two indeterminate forms here, right, you can try to manipulate such that you get the forms here, as will be demonstrated in the tutorial questions. Okay? So we're going to maybe use L'Hopital's rule to evaluate the three limits here. Okay? So let us go through together. So first of all, you always check whether you get the condition for L'Hopital's rule. So you can see this one, clearly you are going to get infinity over infinity. Because 2x squared, you sub in infinity, is going to give you infinity. Then the same thing for this x squared term here. So therefore, you just use L'Hopital's rule. So L'Hopital's rule, I just put L prime h. Okay? So by L'Hopital's rule, so this limit, right, becomes, so you differentiate the numerator. So you get 4x minus 3 divided by 2x. Agree? But this thing, you sub, still give you infinity over infinity. So then you repeat L'Hopital's rule again. Because infinity over infinity can use L'Hopital's rule. So you can just keep on using until you find the limit or you get a form that you cannot use. So therefore from here, differentiate again, you're going to get 4 over 2. So the limit is 2. That's the limit. If you use factoring and dividing off, in this case, right, because x goes to infinity, you can also use dividing by largest power of x. If you do dividing by largest power of x, right, you will notice that you get 2 divided by 1, which is also 2. Okay? So this is legit. Any questions with the usage of L'Hopital's rule? Okay, so actually this is quite straightforward. So for the second expression, now if you try to sub in, you notice you get 1 plus 0, right? Because it's 1 plus 1 over infinity. So it's 1 plus 0 to to the power of infinity. So therefore, this is 1 to the infinity. 1 to the infinity. It's an indeterminate form. Okay? So therefore, directly you cannot use L'Hopital's rule because there's no fraction in the first place. But there's a trick that we can make it into a fraction. That is, you see, function of x to the power of function of x. So how to bring the power down? You ln. Okay? Just apply log. Then you're going to bring down that thing. So therefore, the trick here is, this limit, let me call L. So L is equivalent to e to the ln. E to the ln. E to the ln means inverse functions. So you don't change the original function at all. Then you put the whole limit inside this. So now becomes limit x go to infinity, 1 plus 1 over x to the power of x. Is that right? Okay. But this limit is the same as if you take out the limit operator and apply to e to the ln of 1 plus 1 over x to the power of x. Same thing because the limit, right, only operates on those expressions that contain x. So you bring out or you bring in, doesn't matter. Because e to the ln, they are just functions. Okay, they are not an expression having x. Right, so this is the same thing. So now, right, you see that we have the ability to bring down this x already. Okay, bring down the x. So now we have, okay, let me just bring down the x from here. So let me just cancel this, cancel. And then the x I bring forward. So x put here. Now you notice that if you were to do substitution, you're going to get infinity times ln 1, right? Which is infinity times 0. So infinity times 0, you cannot use L'Hopital's. But you can easily make it into 0 over 0 or infinity over infinity. Okay? So which means all we need to do, now let's evaluate this part. This part. Okay? So this part, we can write it as x ln 1 plus 1 over x can be written as ln 1 plus 1 over x divided by 1 over x. It's the same thing. When you divide by 1 over x, right, it's the same thing as you multiply by x. But when you see this, right, you notice this guy is actually, when you sub in the x infinity, x is infinity, right, you're going to get 0 over 0. So from here, right, equals to 0 over 0 as x approaches infinity. So this is the license for you to use L'Hopital's. So now you can use L'Hopital's on this expression now. Okay? So therefore we have the limit as x goes to infinity of this expression. Okay? So next we just differentiate numerator and denominator. So because this guy, ln 1 plus 1 over x, right? So we're going to have 1 over 1 plus 1 over x first. Okay? Differentiate ln anything, just 1 over that something. Then after that you have to use your chain rule. So chain rule, differentiate 1 gets 0. Differentiate 1 over x, you're going to get 1 over, minus 1 over x squared. Okay? So that's for the numerator. Then the denominator, very nice, 1 over x. So you're also going to get minus 1 over x squared. Any objections? So this one using L'Hopital's, maybe I should label clearly. Okay? So from here, you do observe that actually the terms divide away. So this will divide away this. So the end result is what? 1 over 1 plus 1 over x. Can I straight away sub in Okay? So 1 over 1 plus 1 over infinity. So the answer is 1. Not finished yet. Okay? Because we just evaluated this exponent. So we just sub in 1 into the exponent. So therefore L must be equivalent to e to the 1. Okay? So therefore the answer is going to be E. Any questions? Any questions? So this is really trying to do some math manipulation using the ln expression so that you can get the form to use L'Hopital's rule. Okay, or else that limit is not so easily evaluated. Can? Okay, so that's the second question. So the last question here. Okay, so for the last question, if you do direct substitution, you notice that you are going to get 1 over 1 minus 1 minus 1 over ln 1. So which happens to be 1 over 0, 1 over 0 minus 1 over 0. So 1 over 0 minus 1 over 0 is undefined in the sense that this is plus minus infinity, then minus of plus minus infinity. So it's effectively infinity over infinity. So it's indeterminate. But this indeterminate form, right, you cannot use L'Hopital directly. So you've got to turn it into a fraction. So you have two fractional terms here. How do you think you can turn it into a fraction? The simplest way is to make common denominator. Just make the common denominator. Okay? So see, so now this limit, right, it becomes, so make common denominator, the first term, right, is x ln x minus the second term, x minus 1, divided by x minus 1 times ln x. So this one is just making common denominator by just multiplying each term, right, with the denominator of the other term. This one I need to explain. So this one is just multiply by ln x over ln x. You see, you multiply this first term with ln x over ln x. Then you multiply the second term, right, with x minus 1 over x minus 1. So that will give you the same denominator, which is x minus 1 times ln x. There, this guy. So then the numerator becomes x ln x minus x minus 1. Okay, fair? Yeah, so when you write it this way, then you notice that if you were to do a sub, right, you are going to get x, which is 1 times ln 1 minus 1 minus 1 divided by 1 minus 1 times ln 1. So therefore this is going to give you, so ln 1 is a 0, 1 minus 1 also 0, so you get 0 over 0. So 0 over 0 you can use L'Hopital already. So which is why we make it into a single fraction. Okay? So therefore by L'Hopital, so then we are going to write the limit. Okay? So from here you differentiate, right? Or you have to use product rule. Okay? So you'll be x 1 over x, because you differentiate ln x, then plus ln x. Okay? You differentiate away the x, then minus 1. Then that's dividing by. So the denominator, if you differentiate, you're going to get x minus 1 times 1 over x plus ln x. Okay, so effectively I just differentiated the numerator and denominator separately. Okay, so we can simplify the expression. So in the end result is just 1 minus 1. So we get ln x divided by. So this is really 1 minus 1 over x plus ln x. Okay, so with that, I think we can try to substitute. So you try to substitute, right, you get ln 1 dividing by 1 minus 1 plus ln 1. Okay, so therefore that's still going to give us 0 over 0. So then we just differentiate 1 last time. Okay, so by L'Hopital again. So differentiate ln x, get 1 over x divided by, differentiate 1, get 0, differentiate 1 minus 1 over x, you'll get 1 over x squared. Okay, then plus 1 over x. Can So this one can simplify. Okay, so this is really 1 over x divided by 1 over x multiplied by 1 over x plus 1. So the 1 over x can be divided away. So then the end result is 1 divided by 1 over 1 plus 1. So the answer is half. Is that right? Yes. Which part? Where? This part? X minus 1. Here. Here? X here? Why? Yeah, I can expand also. Yeah, I didn't. So, but I did what? I thought it's here. It's here, right? So then what's the problem? Can, right? Expanded, right? Any other questions? Okay, good. Yeah, so I hope the demonstration for L'Hopital's rule is sufficient now, right? You can use this limit evaluation technique in tutorial 3. Yeah, so that's the end of topic 3, okay? Yeah, so if you are interested in the how neural networks train, okay, you can watch this video here, right? And it's really just using a messy chain rule. Yep. Yeah. Okay, so that's for topic 3. Now we're going to begin on topic 4. So now we are jumping from derivatives to integrals already. Okay, so that's basically about it for differentiation. You have done all the, you have gone through, I believe, most of the differential calculus stuff. Okay, so now we're going to change sides to the opposite of differentiation, which is integration. Okay, so once again, the culprit is Isaac, right? So he too free. Besides trying to find the slope of the tangent, he also too free go and find the area under a curve. Area between a curve f of x and the x-axis, for example. Okay? Yeah. So basically, after he solved the tangent problem, then he thought about the area problem. Okay? Yeah. So now, what we want is basically just, if I give you a function f of x, right? Any function. Then I give you the interval a to b, a to b. Then I ask the very logical question, how can you find the area under the curve above the x-axis? Okay, so this is the motivation, this is what Newton is trying to find, right? So then we just use a very rudimentary, or very, brute force method. So the brute force method is obviously to draw a lot of rectangles. Okay, that's what you see here. Now you see, if I try to crudely approximate the area, right, by 5 rectangles, can see 1, 2, 3, 4, 5, 5 rectangles. Okay, obviously you can see that there's a lot of error, right? This white space, this white space, this white space, all error. Then after that you have this bunch sticking out of the curve. Then obviously that's going to cancel off some of the errors here. Okay, but nevertheless, going to have some errors. But let's stick with this crude 5 rectangles for now. Now you see, what is the area of each rectangle? Very easy to calculate, It's just height times width, what? Correct not? So what is the first height of the first rectangle? F of x naught, law. F of x naught times delta x. Okay, so obviously for simplicity, we can put all the width of each rectangle being the same. So that is just delta x. You see, delta x, Okay, so therefore, first rectangle, f of x naught times delta x, plus second rectangle, f of x1 times delta x, and so on so forth. Okay, all the way until the last rectangle, right? F of x at n minus 1, let's say in this case, n equals to 5, so x4 times delta x times the width. Okay, so all these are just height times width. Okay, so obviously I can sum them up, right? So I just use the summation symbol, right? F of x I minus 1 times delta x. Delta x is a constant in each term. You see? So sum from what? Sum from I equals to 1 to n, because altogether I have n rectangles. Is that okay? Can Okay? So therefore this is my area, or the crude approximation of the area. Any questions with this? Good. But I can also choose to use the right endpoint. Okay, because this one, I use the height which is at the left of the rectangle. Okay, but I can also use the height at the right of the rectangle. So which means if I choose the height to be such that it is on the right of the rectangle, then you will see this instead of this. Okay, you can see the difference, right? So on the right of the rectangle, if you have an up-sloping curve, right, then you're going to overestimate instead of underestimate. Okay, but regardless, you're going to have some errors. Okay, but it is still the same thing, right? Height times width. So height times width plus height times width and so on and so forth, sum them up. But you notice that in this case, I have f of xi instead. Okay, because you start from x1 ma, x1 to xn, x1 all the way to xn. Okay, so I have f of xi here instead of f of xi minus 1. Okay, yeah. Then of course this is not the only two ways what, use the left and use the right. I can also choose to use the midpoint. So clearly the midpoint will be a lot more accurate. Okay, but later on you will see that actually we just choose the right endpoint, which is the easiest to use, because eventually we are going to increase the number of rectangles. Okay, so what is the exact area? Now here comes the limit again. Obviously the exact area is I want to have infinity rectangles. Agree or not? So if I have each rectangle being of infinitesimally small width, the width is not 0, okay, it approaches 0. So that means I want my number of rectangles to approach infinity. Okay, so all I need to do is to evaluate the limit of this sum or this sum. Okay, doesn't matter which lah, right? I can use left or right endpoint, doesn't matter, but right endpoint is probably easier, as you'll see later on. Okay, then I'm going to approximate, or rather I'm going to calculate the exact area, okay, by taking this limit. So once again, it's a limit operator. Can Okay, so what is an integration? Is exactly evaluating this limit. Integration means evaluating the limit of infinity rectangles on a sum of areas of rectangles. That's it. That's integration, right? Which is not so critical. Actually, the area, right, you can have the height evaluated at any x in between, for example, x1 to x2. Let's say now you want to find the height of this rectangle, right? So you can use any x from x1 to x2. So that I call that x2 star. Okay, or generally xi star, right? Because just now we demonstrated what, can use left, can use right, can use midpoint, or in fact can use any x in between. Okay, so they call that xi star lah. Then this sum, they call it a Riemann sum. Riemann sum. Then by the way, this Riemann guy, Bernard Riemann, he's also another smart guy. Okay, so therefore this is called a Riemann sum, and the limit of the Riemann sum is exactly the integration. Okay, so integration is all about finding exact area. Can So obviously we will need to go through some examples on how to find the limit of a sum. Okay, so we're going to be using these series formulas here, right? All this I won't go through lah. Okay, this is basically the sum to first n terms. So if you sum 1 means 1 plus 1 plus 1 plus 1 for n times, right? Then obviously you get n. Okay, if you sum the first I terms, when I goes from 1 to n, so 1 plus 2 plus 3 plus 4 all the way to n, then we can show that you're going to get n times n plus 1 over 2. I square, you're going to get this. I cube, you're going to get this. Okay, so if you want to know the derivations, go to brilliant.org. Okay, by the way, this thing is called arithmetic progression. This one, 1, 2, 3, 4, 5, arithmetic progression. Okay, so it's called AP, the sum to n terms of an AP. You can find out the derivation on those. Okay, so now let's try to evaluate this sum or this integral. So first of all, right, we define delta x first. But delta x is very easy to define. Now, for example, let's say you want to integrate from 0 to 1. What does that mean? That means left limit must be 0, right limit must be 1. Okay, and because you got n rectangles, so you want even spacing, so it must be 1 minus 0 divided by n. Okay, so delta x is always b minus a over n. Let me write. This delta x is always b minus a over n. Always. Okay, so in this case, right, b is the right endpoint. So this is b, and a is the left endpoint. Need not be 0 and 1, can be any other number, right? But just represent them as a and b respectively. Okay, so you can see this is really 1 minus 0 over n. Okay, so that's how we calculate delta x. Easy. So then what about the xi star? So because we use right endpoint, right Riemann sum. Okay, so right endpoint here. Okay, so right endpoint means your xi star must be xi. Let me go back to the slide. This one. Can you see? Xi, f of xi. Can so xi star is at the right, so xi. If it's the left, then it will be I minus 1, xi minus 1. Can you see? Okay, so what is xi? Xi is x naught, but x naught, right, is the first left endpoint. So this x naught, right, is actually always A. So let me underline. This x naught, right, is always A. Extreme left endpoint. Okay? So then it must be x naught plus I delta x, correct or not? Because I is the number. Let's say if you have x1. x1 means what? You go from x naught, you go one step, which is plus 1 times of delta x. Okay? So this part, let me just write a few terms here. So this part. So obviously you see that x1 equals to x naught plus delta x. So let's draw the number line and you'll see. So number line. So let's say this is x naught equals to A. So then you jump one step, delta x, then you hit x1, then you jump another step, then you go x2, and so on and so forth. Okay? So every gap must be delta x. So you can see that x2 equals to x0 plus 2 delta x. Okay? And so on and so forth. Okay? But then because in this case, A is equivalent to 0. You see? For this particular example, integration from 0 to 1. So A in this case is 0. But delta x is 1 over n. So therefore I have I times 1 over n, which will give me I over n. Okay? So hold on, I change a bit of color, you'll see. So this thing is here. Yeah, then after I evaluated my xi, so what I need to do is to sub into the sum already, the right Riemann sum, okay? But what is the function? The function here, the integrand function, the function that is inside the integral, is just x. So let me underline. See this guy, the function. So the function here is this function, f of xi star. In this case, equals to f of xi. But f of xi is x, right? Equals to xi. Because the function is f of x equals to x, Correct or not? There, f of x equals to x. Can you see this guy? Can So then I just sub in. You see, this is xi. So I just sub in xi. Then my delta x, I evaluated already. 1 over n. 1 over n. Okay, and then xi, I also evaluated already. I over n. So I over n times 1 over n. So I get I get I over n square. But I over n square, the 1 over n square got nothing to do with I, what? 1 over n square is a constant. Constant in I lah. So therefore I can factorize it out. So then I just sum the first items. Okay, so I think you can see where this is going. This sum, right, we use this formula, the second formula. So you just replace the sum, this sum, by this formula. You see? Okay, so this one from the previous slide. Then after that, remember the integral is taking the limit on the sum here. So I take the limit on this 1 over n square times this. Okay, then after I multiply out, so you can see there's an n square. N square divided by n square, divided by 2, I get half. Then there's an n over 2n square, I get 1 over 2n. So this expression, I take limit, very simple. Sub in n equals to infinity. First term is half, second term is 0, because it's 1 over infinity. So I notice that the integral gives half. And that's obviously correct, what? Because half is 1 times 1 divided by 2. So you notice that as I use infinity rectangles, I get the logical area of half. Obviously, if I ask you to find the area under this y equals to x curve, right, from 0 to 1, you straight away can tell me it's half. You don't even need to do all this. Okay? But of course, we are demonstrating this process will be able to give us the expected answer. If I give you a curve, then you got no choice but to use this process. Okay? Since you cannot use simple area formulas to find the areas of curves. Any questions? Yes? Sorry? Oh, xi star. The deal with xi star, right, is that xi star can be anywhere from xi minus 1 to xi. Okay? Because if I use the left end point, right, then you notice I'm using xi minus 1. I always evaluate the height at the so-called the point that is on the left. So therefore this is xi minus 1. Then if I use the right end point, that means I'm using xi. But I can also use in the center, what? You see? The midpoint. So therefore xi star can be anywhere. So this xi star, you can use anywhere. You can use this x, this xi star, you can use, for example, this point. You can also use this point. You can use this point. You can use this point, this point, this point. It doesn't matter. Okay? Why it doesn't matter? Because eventually if you take limit, right, it doesn't matter where you take xi star to be already. Because your width of each rectangle is going to be infinitesimally small. So it's going to squeeze towards xi star. So you don't care what is xi star anymore when you take the limit. Is that okay? Okay, very good. So therefore, this is the whole process. Okay, so obviously, first time you see this is kind of messy, right, and kind of daunting. Okay, truth is later on, we just use a table to find the integrals. But obviously, we will need to know how this comes about, just like when we evaluated the limits, giving us the derivatives. Okay, so we have to understand the origins of the knowledge that we apply. So now, I'm going to demonstrate for x squared. This one you cannot use formula. You cannot use simple area formulas to calculate already. Okay, you have to go through the pain. So same thing, nothing much different from just now the earlier example. Okay, let's go through together. First step, delta x. But delta x is always b minus a over n ma. Okay, but what's b? b is 3 what? a is 1. So hence it's just 3 minus 1 over n. So delta x is just 2 over n. Any objections? So I just follow the same procedure. So next, I want xi, okay? Because I use right end point. Once again, right end point. Okay, so basically you just have to worry about right end point. So xi equals to x naught. Okay, should we put a lah? No need to waste time with x naught lah. Okay, a plus I times delta x. So what's a? A is 1 plus I. Delta x is 2 over n. So therefore is 1 plus 2i over n. So I found my xi. Now, I need to compute the sum. So second step, sum. Okay? Sum of I equals to 1 to n. F of xi times delta x. Height times width. Sum all the height times width, area of rectangles. So now I need to know what is my f of xi. But f of xi is this function what? I'm trying to find the area underneath the x square function. So therefore, f of x equals to x squared. If f of x equals to x squared, f of xi must be xi. So sum. So just sub in xi squared. Okay, then delta x is this, right? Okay, maybe I put delta x first. So then I'm going to sub in the xi squared. It's going to be 1 plus 2i over n whole thing square. Then because delta x is 2 over n, so I sub in also. Any objections? Okay? Yeah, so I can expand this. Maybe I expand first. So this guy is going to give me 1 plus, so this is a square, so we have 1 plus 4i over n, because it's 2i over n plus 2i over n, 4i over n plus, so this is 4i square, okay, because you're going to square this, over n square, okay, then times 2 over n. Is that right? So you notice that I've obtained the Riemann sum here already. Okay, this is my Riemann sum answer. You can see from the solution provided. But certainly I want to know the exact value. So I'm going to perform the limit operation now. Okay, so from here you actually have three terms, right? So the first term, okay, so you take the limit. So this is the integral. So integral from 1 to 3x squared dx. So that's equivalent to taking a limit on the sum, on this sum. Okay, so this sum I'm going to expand, right? So you observe that I'm going to have, okay, let me write one more step just to be very clear. So the limit on the sum, right, the first term is just 2 over n. Okay, so bracket 2 over n. I multiply that 2 over n in. So then plus 8i over n square plus 8i square over n cube. Is that right? So then this limit, right, actually when you limit of this sum, is the same thing as the sum that is applied to each and every term. So you take the limit, n goes to infinity, n goes to infinity. So now you have your, firstly, 2 over n sum 1. Sum all the ones. Okay? Sum for how many times? Sum for n times. So this is I equals to 1 to n. Then plus the second term. Now the second term will be 8 over n squared because you can factorize out the constants. Then this becomes sum of I. Okay? Then the last one is plus 8 over n cubed. Then you sum I square. I break it up so that I can use the formulas clearly given in the earlier slide. Okay? So then from here, right? So before I take the limit, so this 2 over n times sum 1 for m times, right? This is just giving me n ma. So it's really 2 over n times n. Hold on, I change color so that you can see which term I'm referring to. Because you 1 plus 1 plus 1 plus 1 for n times. So therefore you just get n. So you're having a 2 there, basically. So plus the 8 over n squared thing. Then this sum I, right? So we just have our formula. N times m plus 1 over 2. From here, n times m plus 1 over 2. So I just plug it in. So this one is the second term. Draw in orange. Then finally, the last term. So this is 8 over n cubed. Then sum I square, right, is a nasty formula. N times m plus 1 times 2n plus 1 over 6. So I change color also. Okay, then I remember to close this bracket. Is that right? Okay, so now basically you can expand the terms. So the first term is actually just giving you 2. First term, I get 2 because it's 2n over n. So the first term is just 2. That will be clear. Second term, 8 over n squared times n squared over 2. Is that correct? Hold on. So it's actually 4n squared over n squared plus 4 over n. So I'm getting a 4. Okay, maybe I skip too many steps. I hear the people laugh. Okay, sorry. I just do one more step. Sorry. Okay, so this is 2 this is obvious Okay, this one 8 over 2 is 4 ma. Then after that, this part is n squared divided by n squared is 1 what? Then plus, this is n divided by n squared is 1 over n. So therefore, this 2 plus, if you sub in the n equals to infinity, obviously you get 4 times 1 what? So it's 2 plus 4. So the third term, I also need to expand out. So you can see the n cube here, then there's an n here, right? So basically, I can cancel off one n. This one cancel. Cancel. Then the cube here also becomes square. So 8 over 6. So let me continue. So 8 over 6 is 4 over 3. Okay? So you notice here, right? You get 2n square over n square. So it's 2 lah. 2n square over n square. Okay, let me just write as 2 lah. Then you get 2n plus n. So 3n over n square. 3 over n. Then plus 1 over n square. Is that right? So therefore, this is what? This is plus 4 over 3 times 2. So it's 8 over 3. Because the rest all zeros already after you sub in. Yes. This one. This one. Oh, because it's 2 over n, right? So because this got no I, I'm summing the I index. So therefore, this 2 over n is a constant. So I can take out of the sum. Then this is just a 1, so I'm left with a 1 inside. I mean, of course, I can multiply in. Then it becomes sum of 2 over n, the first term. Oh, same thing. So you see this guy, right? The I must be inside the sum. You see, the I must be remaining inside the sum because you are summing with respect to I. Okay, whenever you see an I, we are summing with respect to I, you cannot take the I out of the sum. But you can take any constant out of the sum. Is that all right? Okay. So if you calculate this, you notice that you get 2 plus 4 is 6. 6 and 2 and 2/3. So the answer here is 8 and 2/3. Any other questions? Any other clarifications? I tell you, you think difficult, right? Looks difficult, right? I realize that for midterms, right? I mean the past batches, they always get this correct. This one is like easy. Really, after you do a few, right? You feel like boring, this one. Really. Now you look at very difficult because first time you learn, right? The process a bit lengthy. Okay. Now, I can tell you the integration of x squared from 1 to 3 is going to give you 8 and 2/3. Okay, so obviously we are going to just use Desmos to get the answer, right? And Desmos can do integration also. Integrate. You see? You just int only. Int. Integrate. 1 to 3 x square dx. You see? 8 and 2/3. 26 over 3 lah, which is 8 and 2/3. Okay, so the area underneath the x square curve is this 8 and 2/3. Okay, yeah, so I think I'm going to stop the class here. Okay, yeah, so tomorrow we will do our tutorial 3. Okay, we'll do tutorial 3. Right, then maybe next week we'll continue with topic 4. So next week we'll definitely finish topic 4. Okay? So your midterms will be from topics 1 to 4. Topics 1 to 4, midterms. Midterms will be in week 8, which is after the term break. Okay, topics 1 to 4. Right, I'll make announcement.